1931. Continental's A40, 37 horsepower. 1958. A Continental O-200 powered Cessna's new 150 trainer. New engines kept coming. But small airplanes kept the old flat, air-cooled idea. Why? Because replacing an engine means replacing the entire world that keeps it flying. NASA's history of light aircraft propulsion points to the Continental A-40 as an early popular horizontally opposed aircraft engine with more than 2 cylinders. It was introduced in 1931. The report lists a displacement of 115 cubic inches, output of 37 horsepower, and a weight of 144 pounds. Those numbers are small by modern standards. Their importance is not. They describe a choice: put cylinders opposite one another, keep the crankshaft short, and let moving air do much of the cooling. In a light airplane, every pound and every piece of plumbing is a decision about what will be allowed to fail, what can be inspected, and what can be repaired far from a factory. That is the question underneath this entire film. Why did this layout remain visible for so long? Not because time stopped. Alternatives arrived. New fuels arrived. Electronics arrived. But an engine is never only an engine. It is a bargain between physics, certification, manufacturing, pilots, and the people who must keep the thing alive. And the bargain began before most of the airports in this story had even been built. The horizontally opposed engine is easy to describe and hard to reduce to a slogan. Picture cylinders lying across from each other, their pistons moving inward and outward in pairs. The arrangement can package power into a shallow shape. It can place cylinder heads in the airstream. It can avoid the complexity of some liquid cooling hardware. But simple is not the same as easy. Air cooling means the engine lives in a changing stream of air. A climb on a hot day, a long taxi, a winter descent, an imperfect baffle, a worn seal, each changes what the metal sees. The design trades radiators and coolant plumbing for fins, airflow management, and a close attention to temperature. NASA's review does not present the old piston engine as a flawless survivor. It describes a general aviation world in which weight, cost, reliability, fuel, and installation all pull in different directions. That is why the engine under a Cowling has endured so many arguments. It was never just a question of horsepower. The early Continental A-40 was followed by other engines in the family. NASA's historical figures include the Continental A-65, another opposed engine, rated at 65 horsepower. The sequence matters less as a catalog than as a record of gradual fit, enough power for modest airframes, familiar maintenance, and a configuration that designers already knew how to mount. Once an architecture is installed in airplanes, shops, manuals, training programs, and parts networks, changing it means changing more than an engine drawing. It means asking an entire ecosystem to learn a new set of consequences. That inference does not explain every decision made in general aviation. But it helps explain why the age of a mechanism and the age of its usefulness are not the same thing. The next chapter is where that usefulness becomes visible, not in an engine factory, but in an airplane that taught countless people how to leave the ground. An engine becomes part of a culture when people stop noticing it. It starts. It runs. It brings students back to the runway. And for generations of pilots, that familiarity had a shape: a small Cessna, 2 seats, tricycle gear, and a Continental O-200 at the front. The National Air and Space Museum says Cessna redesigned its 12140 line for the two-place market and designated the new series the 150. The prototype first flew in September 1957, the type certificate followed in July 1958. The museum identifies a Continental O-200 engine in that story. That does not mean every flight school shared one identical experience. Aircraft change. Engines are overhauled. Airframes live complicated lives. But the pairing gave the public a durable image of small airplane flying, a light, direct drive, air-cooled engine turning a fixed-pitch propeller on a trainer built to make the first hours of flying less mysterious. The significance is visual as much as mechanical. An airline passenger sees a turbine through a window only as a blur. A student pilot can hear every change in a piston engine. The throttle goes forward, the note changes. Mixture changes, the note changes. Airspeed comes alive, the note changes again. The engine becomes part of the lesson. That kind of familiarity creates an invisible infrastructure. Pilots learn the vocabulary. Mechanics learn the failure modes. Instructors build procedures around what the airplane tells them. A new engine cannot compete only on a test stand, it must become legible inside that whole human system. Continental's own history page calls the O-200 a 100 horsepower engine and associates it with the Cessna 150. The independent museum record is the stronger historical anchor here. The manufacturer page is retained for product chronology, not for a claim of unrivaled importance. The training airplane made the lineage visible. But visibility can hide a deeper problem. The same design that feels dependable can also begin to look frozen in time. By the late 20th century, the light aircraft engine faced a problem that no cylinder redesign could solve alone. The market around it changed. NASA's propulsion history describes the dramatic downturn in United States general aviation airplane production after the late 1970s peak and treats that collapse as a central condition for propulsion development. The important point is not a single chart point. It is the break in momentum. A smaller new aircraft market means fewer opportunities to spread the cost of a new engine across large production runs. That is where the old engine acquires a second life. It is no longer only the engine chosen for new airplanes. It becomes the engine already installed in airplanes. The engine with known tools, known service bulletins, known overhaul practices, and known limits. AOPA reported in 1998 that the general aviation industry had been looking for ways to revive itself and described NASA-linked work on new propulsion ideas. The article also recalled Continental's Tiara program as an earlier attempt that did not succeed in the marketplace. That is a useful correction to the easy myth. The old engine did not survive because nobody tried to replace it. New concepts were imagined, certified, tested, and argued over. Some reached hardware. Some carried real promise. But every new path carried its own cost in engineering, installation, certification, support, or market acceptance. A slow market makes radical replacement harder because novelty needs volume to mature manufacturing, train mechanics, generate part support, and prove reliability in ordinary service rather than on a demonstration flight. This is not an accusation against any one manufacturer. It is a systems observation. In aviation, a machine must survive the factory, the regulator, the owner, the mechanic, the insurer, and the weather. If it fails any one of those tests, a technically interesting idea can remain a footnote. And Continental's footnotes are more interesting than the legend suggests. In the conventional story, the old piston engine sits still while the future goes somewhere else. NASA's archives tell a more complicated story. In 1980, a NASA-hosted Teledyne Continental study examined lightweight diesel engines for general aviation. The study did not merely speculate. It considered engine configurations, performance, stress, weight, cost, and aircraft applications. That is the language of a serious alternative. Diesel cycle ideas offered potential advantages in fuel use and fuel availability. But an aircraft engine is not judged by one line on a fuel consumption graph. It must carry the weight of its cooling system, its injection system, its turbocharging if required, its materials, and its certification path. NASA's 1998 Propulsion Review also discusses alternative concepts in the long history of light aviation, including Continental's Tiara effort and liquid-cooled Voyager work. The report's value is restraint. It frames these ideas as trade-offs, not as evidence that any old architecture was automatically obsolete. The dream of a better engine is easy to understand. An engine that burns a different fuel. An engine that sips less. An engine that behaves more like a modern automobile power plant. The difficulty is that general aviation is not an automobile market. Aircraft operate in thinner air, face tighter weight margins, and live inside a certification system built to make failure extremely expensive. The technology that wins in that environment is often not the one with the cleanest promise. It is the one whose benefits remain visible after every new hose, sensor, heat exchanger, maintenance interval, and approval document has been counted. That does not make the alternatives irrelevant. Their existence is proof that Continental's lineage was never a passive relic. It had competition from ideas that were genuinely different. The reason to remember those ideas is not to laugh at them. It is to understand the cost of making the next engine truly new. And sometimes, the most revealing innovation is not a new engine at all. Sometimes it is a new way of seeing an old one. George Brawley's question began with a gauge. Smithsonian Air and Space reported that, after buying a Beach Bonanza in 1991, Brawley installed instrumentation to measure exhaust gas temperature for each cylinder on its Continental IO 520. As he leaned the mixture, the 6 cylinders reached their peak temperatures at widely scattered points. That observation is small enough to fit on one display. It opens into a much larger idea. An engine described by a single RPM needle and a single fuel flow number can appear to be one thing. Measure each cylinder separately, and the machine becomes a collection of related events, different temperatures, different fuel distribution, different combustion timing, different stresses. Smithsonian's account follows Brawley and collaborators as they investigated mixture distribution and developed calibrated injector concepts. It also reports their use of more detailed engine monitoring. This is not a blanket operating instruction. It is a historical case study, written about a specific group, a specific aircraft engine context, and a specific argument within general aviation. That limitation is the point. The film is not telling a pilot how to operate an engine. The approved manuals and data for a particular aircraft remain the authority for that aircraft. What the episode does show is how an old-looking machine can contain new questions. In Brawley's case, a more granular measurement did not magically make the engine modern. It made the engine less simple. It exposed variation where folklore expected uniformity. This is one reason legacy machines can remain intellectually alive. A design may be old, yet the way people observe it can change. New sensors do not erase old engineering, they make its hidden behavior visible. The era of the single gauge had not ended. But it had been challenged by 6 separate lines of evidence. It is tempting to call an old engine durable and leave the thought there. But durability is not a property that sits inside aluminum by itself. An engine lasts because someone can inspect it. Because someone can find a part. Because a manual exists. Because a mechanic has seen the problem before. Because an owner can understand the cost of an overhaul. Because an airframe was certified around the dimensions, cooling, vibration, and output of that engine. NASA's history places the major Continental and Lycoming opposed engine families inside a general aviation lineage that reaches back to mid-century design work. That is not a verdict on which company was better. It is a clue about accumulated compatibility. Over decades, compatibility becomes a form of capital. The capital is not only money. It is a memory distributed across hangars, a torque value written down, a tool on a shelf, a mechanic's warning, a service instruction translated into habit. This is the hidden side of the word legacy. It can mean inertia. It can also mean support. The same installed base that makes change difficult can make continued operation possible for owners far from a major factory. There is a cost to that endurance. Old architectures ask for attention. They ask pilots and mechanics to respect heat, mixture, vibration, and inspection. They do not absolve anyone of maintenance. They do not turn every old airplane into a museum piece that will run forever. But they explain why the absence of revolution is not the same as the absence of work. The work moved into maintenance, measurement, certification, and incremental improvement. It became less visible than a new engine unveiling. And because it was less visible, it became easy to call it nothing. The final answer is not that Continental beat the future. It is that the future of small airplanes had to negotiate with everything that was already flying. So what happened to Continental? The honest answer begins by rejecting an easy ending. Continental's history is not a clean line from innovation to decline. It includes early opposed engines, engines that became familiar through light aircraft, alternate propulsion studies, electronic control efforts described in company material, and continuing arguments about fuel, measurement, and certification. The engine that built America's small planes did not remain visible because it had escaped history. It remained visible because history kept giving it jobs to do. NASA's account of the A-40 reminds us that the opposed engine idea was already established in the early 1930s. The Cessna 150 story shows how one branch of that lineage became part of flight training. The diesel studies and other alternative concepts show that the old engine was never the only future being considered. And the IO-520 instrumentation story shows that even familiar hardware could reveal new complexity when someone looked cylinder by cylinder. Put together, those facts suggest that endurance in aviation is not a victory of the past over the future. It is a continuing negotiation between a design's physical virtues and the world built around it. That is why the sound at a small airport matters. It is not only nostalgia. It is the sound of a system still operating, metal cast long ago, a mechanic's knowledge, a student's first lesson, a regulator's paperwork, and a propeller taking one more turn into the air. The engine did not outlive its era by standing still. It outlived its era because the era never completely let it go. End tag over moving runway lights, the machine remained. The system grew around it.